Hello and welcome to Unapplied Maths, the maths show where we have a tenuous relationship with truth and accuracy. Speaking of which, today we're going to be answering the question, why did my physics teacher lie to me so much? And in fact, that's the question that turned me off physics in the first place and got me started in mathematics. So let's have a look at one of the biggest lies ever told to a physics student, and that is going to be the derivation of the pendulum formula. So for our pendulum formula, I'm going to start by drawing myself a pendulum. For this, I'm going to take my vertical as the vertical pendulum and draw a bob coming off at an angle, and I'm going to say that that angle is theta, and I'm going to draw my bob as a little circle here. And like any good physicist, we need to turn this into a force diagram. So let's add on the base forces, and then we'll think about how that converts into component forces. So the force for this one is principally coming down, and that is the weight force. And if we say that gravity has the constant g with a mass m, then this force will be mg. And there should also be a tension in the string pulling us back towards the centre of the pendulum. I'm not really bothered by the tension in the string for this derivation, but we might come back to that later on. So that is the description of the pendulum and the base force, but I reckon the important things going on here are actually the components of force. So for this, we need to break down this mg into two components, and those components are going to come out radially and at a normal. So we've got these two components here, one going in that direction, one going in that direction. And you'll notice that the component of force that is radial should be balanced by the t, and that is because the bob doesn't move towards the pendulum, doesn't come away from the pendulum, it just stays in a circular path. And therefore, the only force that's really going to be affecting the direction and the motion of this pendulum is going to be this perpendicular component. So let's see if we can work out that perpendicular component. Using similar triangles, I notice that this angle is theta, and therefore this angle must also be theta. And therefore, if the hypotenuse component is mg, we can say that this is going to be mg sine theta. Fantastic. At this stage, I reckon we can use a little bit of Newton's laws. In fact, I'm going to go with Newton's second law of motion that says the force is proportional to the acceleration, the F equals ma in fact. So I'm going to say that F equals ma, and I know that the force is only in the perpendicular component. The force is therefore mg sine theta, and the ma is ma. I don't know what the acceleration is yet. I'm trying to find the acceleration. And therefore I can cancel out my m's, and I'm left with acceleration is equal to g sine theta. Couple of problems with this so far, and that is the acceleration is going to be in terms of displacement and time, whereas I'm relating it to theta, which is the component of the angle of the pendulum. So what would be really nice is if we could change this acceleration not from a lateral acceleration in a straight line, but instead a radial acceleration. Essentially what I'm trying to do is convert it into something to do with theta. So for this, we might need to consider how theta relates to the arc length going around the outside. In particular, we could say that if I've got a pendulum of length L, so I've got the force T, and I'm going to give the length of that as L. With my L, I should now be able to say what the radial component of this motion is. And you might notice here that this is actually just a sector of an arc. So if I draw this to one side, this might make it easier to notice. I've got a pendulum moving with L, an angle measured in theta. I'm trying to calculate S, the displacement in that arc. And because theta is measured in radians, as everything should be, this S will just be equal to L theta. So S is our displacement. So we can take the velocity of S by saying S dot and that should be equal to the derivative of this side with respect to time. Well, L is a constant, so that remains. Theta will be affected by time, and so this becomes theta dot, that is the first derivative, the angular velocity, if you will. But just as easily, I can then take s dot dot, the second derivative of the displacement, which would then just be equal to L theta dot dot. But hang on a second, this s dot is also known as a. That is my acceleration in that radial component. And therefore I can replace that a with the L theta dot dot. And that leads me to the calculation that g sine theta is equal to L theta dot dot. Or we prefer generally to rearrange this and say theta dot dot is equal to g over L sine theta. Now, we've got a couple of options here as to what we do with this equation. We'll notice, first of all, it's a differential equation. That is where one variable is related to its own derivative. Here it's a second derivative, so that makes it a second order differential equation. And we learn how to solve some of these in maths lessons, so in physics lessons, but we could take the auxiliary equation from this if you liked, and that would give you something like m squared subtract g over L. Oh, hang on a second, sine theta. That's not going to work for us, is it? So I can't make an auxiliary equation that has a sine theta in it. Don't worry, we've got a trick up our sleeves. What we're going to do for that sine theta is draw a quick graph of sine theta that looks like that. And you might notice that in this section over here, if we just focus on this area, sine theta is actually asymptotically equivalent to a straight line in that section there. So if this is my line theta, and this is my equation sine theta, we have a lovely trick where we can just say that sine theta is equal to theta. So sine theta equals theta, and that's only really going to be true in some places. The point of convergence of this asymptotic is around about 15 degrees. So we say theta has to be less than 15 degrees. It pains me to write a degrees in this calculation, but I am trying to make this video for physics teachers, of course. Naturally, I would prefer to say something more appropriate like pi over 12. In fact, I'm going to write that instead. Theta has to be less than pi over 12. And then we can come back to the calculation that we had before, and now we've got this sine theta, which has become theta, and therefore my auxiliary equation has just turned into m squared take away g over L, which is then equal to 0. Hang on a second, we've made a mistake. Let's go back and track that mistake. Did you notice the direction of this motion? I've got this motion coming down back towards the centre, and therefore this theta is actually measuring how much it's getting smaller. So let's just fix that very quickly and track our changes through and say this mg sine theta should have been negative, which means the force is negative, g sine theta is negative, g sine theta is negative over this side. That becomes negative g over L sine theta, which turned into negative g over L theta. That became a positive, and now that has become a negative. Oh, goodness me. That's just made it even more confusing when doing the auxiliary equation, though, because now we've got an imaginary component of this square root, which means our equation should take the form something like a e to the I square root g over L plus bi to the square root g over L, and it all gets a little bit messy. So rather than doing the auxiliary equation, let's do this a bit like a physicist would. And that is to take a bit of a guess. If I'm looking for a function that is equal to its own second derivative, well, there's not many functions that fit that criteria. Can you think of a function that is equal to its second derivative, check this out, and the negative version of the second derivative? How about if we just test cos of theta? Does that work? Well, the first derivative of cos of theta is negative sine theta. The second derivative of cos theta, therefore, is equal to negative cos theta. And hey, that has very nearly fit my pattern at the top. The only difference is that I haven't got the negative g over L, so I would need to make use of the chain rule to make this work. And therefore, like a good physicist, I found my solution. Cos of the square root of g over L, theta, forgot the variable. Well, of course, that's a mistake. It shouldn't have been a theta because the derivative here is happening with respect to time. So let's just fix that error before anyone notices in the comments and say cos square root g of L over t. If you've already typed your comment in the comment box below, just leave it there. It helps with the engagement. So this is my value then for this unknown function of theta, which means I can set that equal to theta. And that has given me an equation then for theta, so this unknown angle for any value of time. Theta is always going to be equal to cos the square root of g over L multiplied by whatever time we happen to take. A really interesting result from this, though, is that the pendulum must always have a constant time period, a constant swing. You'll notice that cos is a periodic function, so it's going to oscillate between two values. Let's have an exploration of the periodicity of cos. So cos is going to be at its maximum, its first maximum, when the input value is 0, which means square root of g over L times t is equal to 0. And it's going to have its maximum output when the input is, its next one when the input is 2 pi, which means we also have the square root of g over L t is equal to 2 pi, and then from this we can calculate what the time period is from one swing to the next, and actually we can just use this second part over here. So the first part, t must have been 0, so it starts at time 0, and therefore it must finish with one time period at 2 pi multiplied by the square root of L over g. You can see here, though, that 2 pi is a constant and g is a constant, the acceleration due to gravity. It's only going to be affected by L. From that, we can then say that the time period of pendulum is always going to be directly proportional to the square root of the length of the pendulum. Oh, a question.
Hey, what was that sine theta bit?
Over here.
Yeah, the sine theta equals theta. That doesn't seem right. It's not theta.
Well, I am glad you asked, because this is actually the crux of the video today, and that is why are our physics teachers lying to us? Of course, all of this is nonsense, what we've done here. All of the calculations, the results, they are unreliable, because they all hinged upon this curious statement that I made very subtly and quickly without anyone noticing, that sine theta is equal to theta. And of course that's absurd. Sine theta is not equal to theta. What about when theta is equal to pi over 2? Because then you're saying that sine of pi over 2 is equal to pi over 2, but sine of pi over 2 is 1. So then you're saying that 1 is equal to pi over 2, and pi over 2 is about 1.6. Well, that's different. We don't like that. In mathematics, we don't like to lie to our students. We like to give them things that are true. So let's see if we can rewind the clock, unfurl the pendulum a little bit, and do this again, but this time without lying. Now, most of what we've said so far is still going to hold. We're still going to make use of the arc length s equals L theta. We're still going to make use of the force diagram and Newton's laws. That's all fine. But it's this part over here where we replace sine theta for theta. So let's start again from that point and say theta dot dot is equal to negative g over L of sine theta. Now that's going to be a little bit trickier to write down. And to make this work, I think what I'm going to do is stop writing it using this Newtonian notation and instead use the d theta dt notation, because that'll be clearer for me. So I'm going to say d squared theta over dt squared is equal to negative g over L sine theta. And in order to solve this differential equation, I'm going to need to multiply it by something to help myself out. And in fact, the thing that I'm going to be multiplying this one by is going to be d theta dt. And what I'm going to be multiplying this one's by is also d theta by dt. Didn't need the dramatic pause there. So I've multiplied them both by d theta dt. So nothing has actually changed with the truth of the statement. D theta dt is never 0, so I'm not multiplying by 0. This is still a valid equation. But it's going to allow me to integrate it so much more easily. So let's take this problem here, and I'm going to integrate both sides this time, and I'm going to integrate them with respect to time, integrate by dt. And we can explore what happens. Let's do the easy side first, shall we? So taking the right-hand side, the dt dt's are going to cancel. So and the constant can come out as a scalar. So this can be written as negative g over L integral of sine theta d theta. Integrating sine theta is very easy. The integral of sine is going to be negative cos. Watch out for that negative there. This is going to give you g over L cos theta plus d for some integration constant d. The left-hand side, that one is a little bit trickier. But what you might notice is I could write a 2 here, and I could take out a factor of a half. And then we've got something that looks awfully like the reverse chain rule, because we've got a function, its own derivative, 2. I can rewrite all of this as the d theta dt squared times by a half. If you're not sure about that, start with this function here, differentiate it, you'll notice that you get back to that equation. And this is going to be equal to that. So I've now got a new way of writing out my equation. A half d theta dt squared is equal to g over L cos theta plus some kind of integrational constant. Let's move over and start again up here. I think if I multiply both sides by 2 and take a square root, that might be a little bit easier to see. So that gives me d theta dt is equal to 2g over L cos theta plus some integration constant d, and then square root of all of that. At this stage, it's going to be a lot easier to calculate the theta and the t from this side. I could multiply both sides by dt and integrate, but wait, this side is written in theta, not in terms of t, so that's not going to be ideal. Let's reciprocate both sides and instead write this as dt d theta is equal to 1 over the square root of 2g over L cos theta plus d. Now I can multiply by the d theta, take an integral of both sides, and that's going to give me one final calculation for t, which I can complete. So t is then the integral of 1 over the square root 2g over L cos theta plus d with respect to theta. Oh my goodness, look at that. Now you might think this is exciting because we are on the cusp of calculating t in terms of theta, which we could then rearrange to get theta in terms of t and have a better version of the pendulum formula than the one these pesky physicists came up with. But this is a really interesting type of function. For aficionados out there, you'll notice this is an elliptic function. So a function that is related to the perimeter of an ellipse. And it is famously unsolvable. Well, that's not quite true. It's famously not expressible in standard algebraic functions. So I can't rewrite this in terms of multiplication, addition, division, exponentiation, trig, logs, that kind of thing. In other words, I'm kind of stuck. That is the answer. I can only express time as an integral of this messy business over here. So it's not ideal, but it's done. It's finished. We have not lied to you. As a mathematician, I can hold my hand on my heart. Oh, question.
Yeah, so is the Earth flat?
What's that?
Is it flat?
No, the Earth's not flat. Why would the Earth be flat?
Well, it's flat on your force diagram.
My force diagram? Oh. You mean because the force is always pointing down? Well, you're right. That is a problem, isn't it? Because the force doesn't always point down. Try telling that to people in Australia. The force should always be pointing to the centre of the Earth. So it's a little bit of a fudge if I tell you that these two triangles are similar, where this one is the vertical at the top of the pendulum, and this one is the vertical at the bottom of the pendulum. For this, we can ask one of my favourite questions to ask students is, what happens if I dangle a pendulum from the moon and let it swing on the Earth? So we're going to need a new force diagram, aren't we? Let's start off with drawing a pendulum to the surface of the Earth. Really, really big pendulum. And I'm going to call this length L again. But then we've also got the radius to the centre of the Earth, R, and that is the centre of gravity of the Earth. That's where the force diagram should be pointed to. Which means when I extend my pendulum up, and again I'm going to extend this more than the 15 degrees or more than pi over 12 because I'm a maverick. When we extend this pendulum up, we're going to have this angle here, theta, but the force should now be pointing towards the centre of the Earth. And that force is still going to be mg, so nothing weird has happened in terms of the strength of the force. Still going to be mg, but the direction doesn't give us these lovely right angles. So let's explore what happens to the component forces. Let's see, components in red. I've got this this radial force coming out, which is still going to be balanced by the tension force of the string. But I actually want to be calculating the component of force that acts in the normal to this one. So I want to be calculating this force coming out here. And that's not going to be so easy to do. I think we're going to need to introduce another angle. And for my other angle, I'm actually going to choose alpha. So let's extend this dotted line here, and we'll say this angle is going to be alpha, and normally alpha would be so small, but now it's going to be relatively significant. And what we want to do is try to understand the geometry of this shape and see if we can figure out what these force components might end up being. So to begin with, it might be helpful to label this length as L as well, because that is the length of the pendulum string. There's the length, there's the radius. And I might go ahead and label this angle here beta as well, because then I can draw this vector, which is going to be the component in the perpendicular direction. So that's actually the same as this one I've already drawn. And from that I can say that the force is going to be mg sine of beta. So the force is mg sine of beta. Well, if I've got the sine of beta, I can calculate beta in terms of theta and alpha, because the whole triangle has to add up to pi. So that means we're going to end up with f is equal to mg sine of pi subtract alpha plus theta. And given that this is sine, I can rearrange that just to say sine alpha plus theta. So that should give me f is equal to mg sine alpha plus theta from the periodicity of sine. And that, I think, is going to let me calculate everything else if I now come back to this part over here. So we have that f is equal to mg sine of theta plus alpha, and by making use of the same ideas that we had earlier on, we can say that f is equal to ma, so this is equal to mg sine theta plus alpha. A we already had earlier on as L times theta dot dot. So back over here, we've got L theta dot dot, oh no, I've cancelled the L's. L theta dot dot is equal to G sine theta plus alpha. and I can rearrange that then to get theta dot dot is equal to g over L sine theta plus alpha. Here you might notice the alpha is a bit problematic. All of the calculus that we did earlier on relied on everything being in terms of theta as a function of time. That alpha is going to throw a spanner in the works. Luckily for us though, we've got a way of calculating alpha using the value we had before. D squared is equal to L squared plus L plus R squared subtract 2L plus R cos theta, because of course we can recalculate this in terms of alpha as well. Using the sine rule, we know that sine of alpha over L is going to be equal to sine of theta divided by d, where d is the square root of this one over here. So when we calculate the sine of theta plus alpha, of course we will be doing that using the double angle formula to give you theta dot dot equals g over L, and this is sine theta, cos alpha, I'll come back to that, plus cos theta sine alpha, and the sine alpha we can then replace with this calculation over here. Cos theta, I suppose we'll use the square root 1 minus sine alpha squared to eliminate that. And then, hey, everything's now in terms of theta, so you can just apply the same problem that we had over here where we multiplied by the d theta dt and we integrated, and then maybe it will come up to an elliptical function, and then we won't have lied to you, and then it will be true. And then the physicists can just start doing this in A level instead, and it will all be true, and we can all relax and calm down. Oh, a question.
Yeah, what's that about gravity?
Huh? What was that?
Gravity. You've got gravity as a constant, but if you've got a pendulum on the scale of the Earth, then gravity is going to be different, isn't it?
Yes, I did say that, didn't I? I said that g was a constant, but of course, if we are now this high out the Earth's atmosphere, this is going to be about 1 Earth's radius away from Earth. So let's just take that g from here and bring it back to here, and we can fix that because we know the calculation for g, don't we? We know that g is going to be equal to the mass of Earth multiplied by the gravitational constant divided by r squared, the radius away from the centre of the Earth squared. And hey, that was our d squared, wasn't it? We've already got d squared over here, so I suppose we could just say that g is equal to m dot big G. Remember, big G is just Newton's constant, and then divide that by L squared plus L plus capital R squared. Capital R is constant. Take away 2L L plus R cos theta, and then it will be true, and we won't have lied. A question.
Yeah, the physics teacher says everything's a bit stretchy.
No, L is not a constant. No, you're right, because, no pendulum is inelastic, is it? I said, so there's going to be, there's going to be an element of stretch in L. So maybe we could say that L times by E for some kind of stretch. And because E will be a function of time, won't it? It will stretch more at some points and less at others. Huh?
Isn't that going to affect the tension?
Yeah, so the more it stretches, actually there will be some differences in tension, isn't there? So tension is now going to be a function of time, and that will also be affecting the rest of it. So we will have some elasticity forces and some. I suppose it's not really going to do a circle anymore, is it? It might be an ellipse, and this. Okay, I'll tell you what. I think your physics teacher might have been right, and maybe we can just say that sine theta is equal to theta. And maybe people who live in glass houses should learn not to throw stones.
Yeah, he also said you can't take a square root of a negative. Is that real? Also, can we do aeroplane wings?
Goodbye.